Conventional antennas. The simplest and most widely used antenna element is the half-wave dipole, which consists of two linear conductors about a quarter wave long, driven by a source at the center, shown thus. Two variations of the half-wave dipole are the quarter-wave monopole and the folded dipole. The pattern of a dipole can be modified by placing a passive or parasitic conductor near it. Although the parasitic element is not connected to a source, a current is induced in it due to the radiation from the driven dipole. The total radiation is the sum of the driven and the parasitic elements. By suitably choosing the length and spacing of the latter, it can act either as a reflector, enhancing radiation in the direction of the dipole, or as a director, enhancing radiation in its own direction. Illustrated thus. An antenna consisting of a driver, a reflecting element, and one or more directing elements is called a Uda-Yagi array, or a Yagi for short. There is a limit to the number of parasitic elements that can be added to a Yagi, since the induced current on a parasitic element becomes progressively smaller as its distance from the driven element increases. It ceases to play an effective role if it is placed too far from the driven element. Yagis are seldom designed to have more than 12 elements. A 7-element Yagi using a folded dipole, thus, period. While a thin conductor can act as a reflector, it is highly sensitive to frequency. The frequency dependence is reduced if a plain conducting sheet is used instead. The effectiveness of the reflecting sheet can be further enhanced if it is bent into two sheets, intersecting at an angle, as shown thus. The resulting structure is known as a corner reflector antenna. The corner reflector has the limitation that even if the sides are infinite in extent, there is an upper limit to the directiveness of the resultant radiation. To reduce wind resistance, the reflecting metal sheets are placed by conducting rods, resulting in a grid-type corner reflector antenna. Other traditional antennas elements are the loop antenna, the horn antenna, and the helical antenna. The loop antenna is used extensively in TV reception and as directional finders. An indoor TV antenna consisting of a dipole and a loop is shown. By flaring the aperture of an open-ended waveguide, a horn antenna is obtained. The horn antenna is used extensively at microwave frequencies, both as feed antennas for parabolic reflectors and as the standard calibration antenna for gain. For communication with satellites and space vehicles, electromagnetic waves with circular polarization is preferred over linear polarization. The helical antenna is a popular CP antenna and has the antenna and was the antenna brought. Okay, well, I'm not going to read that. So then there's some pictures of different antennas. Typical gain and bandwidth of conventional antenna elements. I guess I'll read the chart. Half-wave dipole, folded dipole, quarter-wave monopole, one wavelength loop, a Yagi, a dipole plus corner reflector, helical antenna, and horn antenna, and it's got the typical gain and typical bandwidth. Two important antenna parameters are the gain and the impedance bandwidth. The gain describes the directional property of an antenna, while the impedance bandwidth describes the range of frequencies within which the voltage standing wave ratio is below a certain value. This value is usually taken as 2 in academia and 1.5 in industry. The abbreviation for voltage standing wave ratio is VWSWR. Excuse me, VSWR or SWR. Both will be used in this presentation. Table 1.1 shows the typical values of these two parameters for the conventional antenna elements described above. One method of obtaining high-gain antennas is to use an array of fed elements, all of which are connected to a source. A linear array is one with the elements arranged in a straight line. The elements can also be arranged in a plane, resulting in a planar array. The element spacing is usually about a half a wavelength. In theory, for a given spacing, the gain can be made as high as one wishes by increasing the number of elements. This figure shows a linear array of folded dipoles. Photograph of a planar array of helical antennas is shown here. Another method of obtaining high-gain antennas is to use a parabolic reflector, with the feed antenna at the focus. The antenna is also known as a dish. For a given frequency, the gain is proportional to the diameter of the dish. In theory, the gain can be made as high as one wishes by increasing the dish diameter. Figure 1.10a shows the 1,000 feet dish at the Arecibo Observatory in Puerto Rico. Figure 1.10b shows the 100-meter, 300-foot dish in Effelsberg, Germany. The former is the world's largest dish, but it is fixed on the ground, although the main beam can be steered to a limited extent by electronic means. The latter is one of the world's largest fully steerable dishes. Figure 1.11 shows the Very Large Array, VLA, in New Mexico, consisting of 27 85-feet dishes arranged in the form of the letter Y. Figure 1.10a, the dish antenna at the Arecibo Observatory in Puerto Rico, and B, the dish antenna in Effelsberg, Germany. Read this caption here. The Very Large Array in New Mexico. Several undesirable features of the conventional antennas can be noted. They are bulky and they protrude from a surface. Moreover, it is difficult to design conventional antennas to perform more than one functions, such as dual frequency and dual polarization. Antennas which do not protrude from a surface are very desirable for fast-moving vehicles such as airplanes, missiles, and spacecraft. In the late 1970s, the military was especially interested in such antennas because they did not interfere with the aerodynamics of these vehicles. Historically, the microstrip patch antenna was developed in response to this need, although its planar profile has been found to be an attractive feature in commercial applications as well. Geometries of the basic microstrip patch antenna. The idea of microstrip patch antennas arose from utilizing. I'll start that sentence again. The idea of microstrip patch antennas arose from utilizing printed circuit technology not only for the circuit components and transmission lines, but also for the radiating elements of an electronic system. It was first proposed by Deschamps, period. However, little attention was paid to his idea until the 1970s. Since then, this class of antennas has been the subject of intensive research and development. There are several thousand papers published on the subject, as well as a number of books. A list of books are given in the reference. The basic structure of the microstrip patch antenna is shown in this figure. It consists of an area of metallization supported above a ground plane by a thin dielectric substrate and fed against the ground at an appropriate location. The patch shape can, in principle, be arbitrary in practice. The rectangle, the circle, the equitriangle, and the annular ring are common shapes. Four feeding methods are shown in figure 1.13. They are coaxial, probe, feed, microstrip line feed, aperture-coupled feed, and proximity feed. Electromagnetic energy is first guided or coupled to the region under the patch, which acts like a resonant cavity with open circuits on the sides. Here's the picture I'll read. The basic structure of the microstrip patch antenna is a ground plane, a thin dielectric substrate, a patch, which can be, I guess, a rectangle, disc, ring, or triangle. Here's another caption and a figure, figure 1.13. 4 common feeding methods of microstrip patch antenna: microstrip line, coaxial probe, proximity feed, aperture-coupled feed. Some of the energy leaks out of the cavity and radiates into space, resulting in antennas. Here's a list, 1.4, advantages and disadvantages of microstrip patch antennas. The advantages of microstrip patch antennas are: number 1, planar, which can also be made conformal to a shaped surface. 2, they are low profile. 3, low radar cross section. 4, they are rugged. 5, they can be produced by printed circuit technology. 6, can be integrated with circuit elements. 7 can be designed for dual polarization operations. 8 can be designed for dual or multi-frequency operations. These advantages make microstrip patch antennas much more suitable for aircrafts, spacecrafts, and missiles than conventional antennas, as they do not interfere with the aerodynamics of these moving vehicles. Figure 1.15 shows a 896 element microstrip antenna array for remote sensing applications. Their planar profiles are to be contrasted with those of the arrays shown in Figure 1.9. Figure 1.16, an array of microstrip patch antennas are made conformal to a wing-shaped surface. Because of the advantages listed above, the microstrip patch antenna has also become the favorite of antenna designers for commercial, mobile, and wireless communication systems. Figure 1.17 shows a patch antenna in a cellular phone. 1.18 shows a base station antenna consisting of patches. Figure 1.19 shows patch antenna arrays mounted on the walls of a building for satellite television reception. Disadvantages of microstrip patch antennas. There are several disadvantages associated with microstrip patch antennas. Number 1, in its basic form, the microstrip antenna has a narrow impedance bandwidth, typically less than 5%. However, various bandwidth widening techniques have been developed. Up to 50% bandwidth have been achieved. It is generally true that wider bandwidth is achieved with the sacrifice of increased antenna physical volume. Number 2, due to the small separation between the radiating patch and its ground plane, the microstrip antenna can handle relatively low RF power. The average power considered safe is a few tens of watts. Number 3, while a single patch element generally incurs very little loss because it is only about 1/2 wavelength long, microstrip arrays generally have larger ohmic loss than arrays of other types of antennas of equivalent aperture size. The ohmic loss mostly occurs in the dielectric substrate and the metal conductor of the microstrip line feed network and power dividing circuit. Material considerations. The metallic patch is normally made of thin copper foil. The substrate material provides mechanical support for the radiating patch elements. It also maintains the required spacing between the patch and its ground plane. The substrate thickness for the basic geometry is in the range of 0.01 to 0.05 free space wavelength. The dielectric constant ranges from 1 to 10 and can be separated into two categories. Number 1, those having relative dielectric constant. Those having a relative dielectric constant, relative permittivity in the range of 1.0 to 2.0. This type of material can be air, polystyrene, foam, or dielectric honeycomb. 2, those having a relative dielectric constant in the range of 2.0 to 4.0. This type of material consists mostly of fiberglass reinforced Teflon. Number 3, those with a relative dielectric constant between 4.0 and 10.0. This type of material can be ceramic, quartz, or alumina. The most commonly used material is Teflon-based with relative permittivity between 2 and 3. This material is also called PTFE, polyterafluorine ethylene.